In this video, we're going to revisit some of the previous concepts that we discussed in other videos and put them together in a way that we can point to a new concept, which is called angular momentum. So to begin with, let's lay out some of the equations that we've seen before and build a table that relates the translational equations to the rotational equations. And so to start with, let's break this into two pieces. So we have our equations for translation and our equations for rotation. Now, on the top row here, I'm going to have force, and I'm going to put this in quotation marks because it's really not exactly just the force for translation, but it's also going to include the torque. And here, I'm going to write the momentum. And again, this is in quotation marks. So, very beginning, we had Newton's second law, and this said that the sum of the forces is equal to mass times acceleration. Now, we saw later when we talked about momentum that we could talk about the momentum of an object by saying that this momentum that we call p vector is going to be equal to the mass times the velocity vector, and that we could relate our equation for force to our equation for momentum by saying that the change in momentum, or delta p, is going to be equal to the force times some delta t. Okay? So if we wanted to know what momentum force imparts on an object, we could say, well, we apply that force for a certain amount of time, and that force times the time that we have is going to be equal to the change in momentum. Okay? So now let's look at our equations for rotation. We saw that we had some analogous concept to force for translation, and that was torque. And for torque, what we said was that the sum of the torques acting on an object is going to be equal to the moment of inertia times the angular acceleration. Okay? And we saw this kind of connection between the mass and the moment of inertia, where the mass tells us how difficult it is to push an object in one direction, how difficult it is to translate an object. And the moment of inertia tells us how difficult it is to rotate an object. Now, we also saw that this torque was itself connected to the force by saying that the torque, if we wanted to find what the torque was acting on an object, if we apply some force to it, is going to be given as torque is going to be equal to R cross F. Or we wrote this more succinctly to say that this is going to be as a magnitude. The torque magnitude is going to be equal to the magnitude of R times the magnitude of F times the sine of the angle between them. Okay? So we saw then how we could apply a force to cause rotation if we apply this force at some distance from the center of rotation. That's how we define torque in terms of force. Okay. Now we have this last corner down here that kind of makes us think that maybe there's another equation, another term that we could add here. And that's what's called the angular momentum. So just as we had some translational momentum that we said P is equal to mv, we also have what's called the angular momentum. And angular momentum is going to be given by L, which is going to be equal to I times omega. And we could even make this vector if we wanted to as well. Okay. So now that we've established this equation for angular momentum, just kind of considering the symmetry of the table that we have here, we also want to connect it to our linear momentum and connect it to our torque. And so the way that we connect our angular momentum to our torque is exactly the same way that we connect the force to the momentum. And that's to say that if we apply some torque over a certain period of time, that's going to impart some angular momentum. And so written in equation form, what this says is that some change in angular momentum is going to be equal to some torque times some delta t. Okay? So that's our connection between torque and angular momentum. But there's also some connection between momentum, or linear momentum, and angular momentum. And that follows the same type of equation that we have right here. So this says that the connection between the linear momentum and the angular momentum follows according to L vector is going to be equal to R cross P vector. Or written as a magnitude, this says the magnitude of L is equal to the magnitude of R times the magnitude of P times the sine of the angle between them. Okay. So just to pause here for a moment and talk about the verbiage or how we describe force versus torque and the way we describe momentum versus angular momentum. Force and momentum are things that we can just say are inherent to an object. We say you apply a force to an object or an object has a momentum. Torque and angular momentum, on the other hand, they need to be defined about a point. It doesn't mean anything to say that an object has some torque, or I apply some torque to an object. You say, I apply a torque about a point. So that is to say that this distance, or this radius that we have here, for both our torque equation and our angular momentum equation are both very important. So now that we've laid out the equations that we have for angular momentum, we'd like to kind of look at how we can describe it a little bit more conceptually. And so the way I'd like to do this is, again, to kind of compare it to linear momentum. So if we had some object and it was moving with some velocity and this had some mass, we would say that this is the way that we would describe the linear momentum. We say that we have some mass times velocity, and this is going to be equal to our linear momentum. Now, angular momentum adds a little piece to this in the sense that in order to calculate the angular momentum of an object, I care about both its momentum and the distance it is from some center of rotation. And so if I wanted to talk about the angular momentum of an object, what I could say is there's some point here, and then the object could be over here, let's say. And again, it could be moving with some mass and velocity. I care when I talk about angular momentum that this is some distance away from this center here. And so if I say that this is some distance r, then when I describe my angular momentum, I say that L is going to be equal to r cross p, which is going to be r times magnitude of r times magnitude of p, which in this case is mv, times the sine of the angle between them. Now in this case, I happen to draw this at a 90-degree angle, but it doesn't have to be at a 90-degree angle. We could in fact have this at some angle that's not 90 degrees. So for instance, I could have some object like this that's moving. This is my mass times velocity. This is our r here. So it doesn't necessarily have to be at some 90-degree angle, but in this example, it happened to be. Now, this is one way that we can look at angular momentum, and that's for a point particle. So this is just some mass. It could be like a ball that you throw. We can also talk about the angular momentum of an object that has, as you say, you call it a rigid body. And so a rigid body is an object that has some physical dimension. We treat these all like point masses. But you can have some object, like some rod that's rotating about a point, where this is solid the whole way. And then what you do is you describe this in terms of a moment of inertia. And so what you would say here is that the angular momentum L is going to be equal to the moment of inertia times the angular velocity. This is going to rotate around this point with some angular velocity. This is the way that we would describe the angular momentum for this object. So in this video, we laid out a table that connected our translation and our rotation in terms of the torque and the force and the linear momentum and the angular momentum. And we also talked conceptually about the angular momentum so we could understand it at a deeper level. In the next video, we're going to consider some examples. Thanks for watching.